So this class will talk about the wettability and the capillary pressure. And this is the basic information before we learn the relative permeability. So this week, we'll cover the wettability and capillary pressure, and then we'll continue to work in the learning and discussing about the relative permeability next week. So we talked about the single phase permeability, right? And we learned the Darcy's law, and we assume that the porous media, the rock, is fully saturated with water or the brine or oil in the case, just within one single phase. But in reservoir rocks, when you produce the hydrocarbon can be in gas phase or the oil, the liquid phase, and also you can have the water, the brine or connate water, right? The formation water. So immiscible fluid, so the water and the oil doesn't mix each other, right? And when you have gaseous hydrocarbon and the liquid hydrocarbon, also they don't mix each other. So immiscible fluids of more than two phases can coexist in reservoir rock. So in that case, we need to define a parameter that can consider the one phase, the permeability of each phase. So we can define the relative permeability, and this is ratio of the effective permeability for a particular fluid at a given saturation to a base permeability. And the range is 0 to 1 because it's defined as follows. So for relative permeability of oil, the effective permeability of the oil divided by the absolute permeability K. So here, large K is the absolute permeability, and the KO and KG and KW is the effective permeability of each phase. O means the oil, and the substrate G means gas, and the water, W is water. And so this relative permeability will be a function of the saturation of the corresponding fluid. So as you can see, for example, let's say here. So here is the gas saturation is 100%. And here is the oil saturation is 100%. Right? And the oil saturation is 100%, then oil permeability, relative permeability is 1. So that means that oil's relative effective permeability is the same with the absolute permeability. And it begins to decrease as the gas saturation increases and also the oil saturation decreases. So it decreases to 0, right? And this portion is called the irreducible oil saturation, or the residual oil saturation. We're going to learn about that later in this class. And also, when you look at the gas permeability, this is the same with the absolute permeability when the gas saturation is 1, right? 100%, and it decreases with the increasing oil saturation. So it's called the multi-phase fluid flow, and the relative permeability is a very important term to estimate the productivity of the hydrocarbon in the reservoir. Because in the reservoir, the water and the oil can exist together. Okay. Then most reservoirs are water wet. Having a water film separating the pore boundaries from the oil. So when you have the water wet mineralogy, this is the water wet. Here the gray color is the water and the oil is the black one. So you can see that the grains are coated by the water. This is the water wet condition. And in some cases the grains are coated by oil. It's an oil wet condition. So in this case, you see the black color means the oil. So the oil is covering, right, and enveloping the grains. and you have a cone water just in the middle of the pore. So this situation is called the water wet, and this situation is called the oil wet. And if you imagine you are flushing, maybe you can inject some water to flow and produce the oil in here. And you can imagine the same case, you are applying it to the oil wet reservoir. Then here the remaining oil will be less than the case for the oil wet case. In the oil wet case, you will have the oil coated by the coating the grains, and they wouldn't be detached easily, right? So oil wet is more straightforward to produce the hydrocarbon, but the oil wet case is difficult. In most of the quartz dominant or the sandstone case, sandstone reservoir, the water wet condition is dominant, and in carbonate reservoir could be a mixed wet case. So you may have a mixed condition with the water wet and the oil wet condition, or the oil wet may be a dominant more than the water wet condition. So far, people have been producing the hydrocarbon mostly from the sandstone reservoir, which is water wet base, but they are trying to increase the level of the production from the carbonate dominant reservoir too. So the fluid displacement and the multi-phase fluid flow behaviors are affected by the capillary pressure and the wettability condition. And capillary pressure data are required for three main purposes: to predict the reservoir initial fluid saturation, and the cap rock seal capacity, and the relative permeability. So for these three are very important information for the reservoir engineering. And the capillary pressure is one of the factors influencing it. Then let's talk about the capillary pressure first, and then we'll move on to the wettability. So capillary pressure, I think we know what the capillary pressure is, right? So you have maybe a tissue or the paper towel. When you dip it in the water, it sucks the water up, right? That's the capillary pressure. And difference in pressure between two immiscible fluids across a curved interface at equilibrium. This is the definition of the capillary pressure. And let's look at this case. You have an oil and the brine, so it's a salty, saline water. And let's say that this is the glass tube. This is hydrophilic. And then this glass tube, because the diameter is so small, the meniscus can bring up the water above the reference level. So this means that pressure across here, you have a pressure of the water and pressure of the oil, and which one is bigger? Across this meniscus, the water pressure is bigger than the oil pressure. And the difference between these two values is called the capillary pressure. Here, because the glass is hydrophilic, the wetting fluid brine, right? And the non-wetting fluid is oil. So wetting fluid pressure, non-wetting fluid pressure minus wetting fluid pressure is called the capillary pressure. Sorry. It's the other way. So wetting fluid pressure minus the non-wetting fluid pressure. And the capillary pressure here is defined as 2 times gamma times cosine theta over the diameter A. So here the A is the diameter. And theta is called the contact angle. We'll talk about it soon. And gamma is the interfacial tension between O and brine. And this is, so we've been using this glass tube as an analogy or the surrogate for the pore of the rock, right? If we expand this glass tube to the real rock pore, then pore geometry and the wettability and the mineralogy will affect the capillary pressure in general. So these are the factors affecting the capillary pressure. Okay, then where the capillary pressure is from, why we have the capillary pressure. I think we've learned this surface tension concept from the high school physics class, right? And the molecule within the media, right, is more stable than the molecule at the interface, right, because of the force equilibrium. So here, when you think about the water in the media, the water is all balanced. The force or molecular level interaction between the molecules are balanced by the surrounding molecules. Right? But here, the molecules only have their neighboring, the water molecules in the liquid phase, so that the force is not balanced here, so that you have a higher energy state, and in nature, the lower energy state is preferred. So they want to minimize the surface area. And this energy is called the surface energy. How strongly these molecules wants to minimize their surface area. So this brings us the meniscus of the water. And when you have a meniscus, always you have a surface tension, and surface tension can affect the capillary pressure. So then let's talk about the wettability concept. So when fluids are in contact with a solid surface, the equilibrium configuration of the two fluid phase, let's say the air and water, depends on the relative values of the surface tension between each pair of the three phases. So in this case, let's say that this is the water and the air and maybe like glass. Then surface tension is acting here in three directions. You have a surface tension between solid and gas. And you have a surface tension between the solid and liquid. And you have a surface tension between the gas and liquid. At this point, the force equilibrium should be satisfied. Then, when we think about the horizontal force, the summation of the all force in the horizontal should be 0, right? So then, gamma SG should be balanced with gamma SL plus gamma LG cosine theta, right? Then if you multiply the cosine theta to this gamma LG, then you have a horizontal force component. And this is called the Young equation, or the Young-Dupré equation. So basically, this equation. So this equation is derived from the force equilibrium. And it tells you that a droplet of the liquid in touching with the other liquid is equilibrated by this interfacial tension between the three phases. The interfacial tension between liquid and gas, and solid and gas, and solid and liquid. Right? So, I think in some case, we can here. So then, if the interfacial tension of the solid and gas here, the force stretching the liquid is larger than the force minimizing the liquid surface, then what happens? So when you look at this one, this force is stretching out the liquid droplet, right? And the interfacial tension between the solid and liquid is trying to minimize their surface. They want to retract the meniscus. Right? So they are pulling each other, right? If these two forces are balanced, if they are the same magnitude, then the contact angle will be at right angle, right? 90 degrees. Because gamma SG is the same as gamma SL. Right? In terms of the magnitude, direction is opposite. Right? It's called a neutral wetting condition. And when this one is larger, then it will be like this. So contact angle will be less than 90 degrees. Right? And if this force is larger, then contact angle will be more than 90 degrees. Does it make sense? So it's all the force balance. So the this one, and for a stable contact, this value should be positive. No. Oh, yeah, this equation should be satisfied. So the absolute value of the cosine theta, when the absolute value of the cosine theta is less than 1, then it's called a stable contact. But if not, if the solid gas interfacial tension is larger than the summation of these two forces are here, so that means in this case, this force is too large, so they are stretching with the bigger force, then the liquid will cover the whole solid surface. So then you have a total wetting. Liquid, solid, and gas. This is the case. And the other case is that when the liquid gas interfacial tension and the solid gas interfacial tension is less than the liquid solid interfacial tension. So that means that this one is this one is much larger than the summation of this one and this one. Right? And then the gas displaces the liquid away from the surface. So then you have a solid, liquid, gas. So I think we all know what Gore-Tex is, right? And you want to have a waterproof, maybe weather clothes, then hydrophobic and non-wetting condition like this is preferable. You want to make this condition so that you can protect your clothes to be wetted. Right? So wettability is defined like this. And when we think about the oil and the water and the rock mineral, there could be 4 cases. Here, the first condition is what? The theta is larger than 90 degrees. Right? So then this is called the oil wet condition. Right? So when you look at here, the oil is intruding more. Right? So the oil is spreaded and covering the more surface than it should be. So then it's called the oil wet condition, and the wetting angle theta is larger than 90 degrees. And neutral wet is when the theta is 90 degrees, the right angle. And if it's water wet condition, then the theta is less than 90 degrees. And the water is covering more area in the neutral wet. So then, when one fluid preferentially covers the surface, it's called a wetting fluid, and the other is called a non-wetting fluid. So in this case, oil wet condition is the wetting fluid is what? Is oil, and non-wetting fluid is water. And in the case of water wet condition, water is wetting fluid, and the oil is non-wetting fluid. So non-wetting fluid and the wetting fluid can be changed depending on the wettability of the rock mineral. 혹시 여기까지 질문? So far, any comment? All right. So the wettability is originated from the molecular level interaction between the solid surface and the fluid. For example, the quartz sandstone grain generally develops a greater molecular force between itself and the water than between itself and oil. So quartz, in the case of quartz, they prefer to interact. They develop a more strong force between water. And clean sandstone, therefore, commonly water wet. And the same grain have been baked at high temperature in the presence of the oil at depth, then its surface chemical structure can be altered, and the surface itself can be coated in a way that it becomes to like more the oil, then it becomes oil wet. So we know that the generally the soil grains are hydrophilic, like the glass or clay or the sand or carbonate. They like the water more than the oil, right? So in very shallow surface, you meet the water wet condition more. But if the rock mineral or the soil has been soaked, submerged, or in contact with the oil very long time, then the oil can develop a coating around the grain. Then it becomes oil wet. So it can be, you frequently meet the oil wet condition in the hydrocarbon reservoir because of the high temperature and because of its history. And properly measure the wettability on well-preserved core, and the core plug should be formed the initial step in choosing relative permeability test methods. So then, capillary pressure. How can we define and estimate the capillary pressure? We've seen the Young equation, and from Young equation, you can derive this Young-Laplace equation. So that you have a meniscus with the two curvature. One is the R1 with the radius R1, and the other is the small radius R2. And the capillary pressure acting on this meniscus is defined as this equation. And it's telling you that as the R1 decreases, then capillary pressure increases, right? And also the R2 decreases and capillary pressure increases. So as the curvature, the radius of the curvature becomes decreased or reduced, you have a small and small bubble, then you have a larger capillary pressure. So actually, let's think about let's move on. And if the radius of the curvature are equal, the R1 and R2 are equal, and capillary pressure can be calculated using this equation, 2 sigma over R. And this R is this one. Radius of the curvature of the meniscus. But it's difficult to measure it, right? So when you, let's say that you have a like straw and you're measuring the curvature and the radius, then it will be difficult to like identify from the picture. So substituting the R for the radius of the capillary tube and the contact angle, then you finally have this equation. So here, the RC, this one is the same with you, RC. The radius of the capillary tube. Huh? Okay, let's move on. So as the difference, capillary pressure increases with decreasing radius, right? Hole through diameter. So when you look at these tubes with different size, A has the smallest diameter and the F has the largest diameter, and the capillary pressure decreases with increasing diameter, right? As you will see. It's very obvious. Huh? And back to the wetting system. So let's look at here. So A and B. In the case of A, is it oil wet condition or the water wet condition? Is oil covering more surface or water is covering more surface? Oil, right? So the A is for the oil wet condition, and the other, the B condition is water wet condition, right? It's very obvious, huh? So then in water wet pores, the meniscus is convex with respect to water. In oil wet condition, it's concave. If it's neutrally wet, then you have a just flat surface, right? Water and oil. Neutrally wet condition. I think this is the explanation for the next graph in the next slide. The pressure at which the injected fluid begins to invade the reservoir is called the displacement pressure. So let's say that you have rock core which is filled with water, then, oil. You're injecting water, and you have to increase to a certain pressure to start to producing the oil. Right? That's the displacement pressure. That's the minimum pressure required to produce the drop of the oil. Then you need to increase the pressure more to produce more and more oil. As the pressure increases, the proportion of the tube fluid gradually reverses until the irreducible saturation point is reached. So as the pressure, inlet pressure here is increased, and you're flushing the water, then you have the water and the oil coming out, right? So that the oil saturation in the rock core will decrease. But at some point, there will be some oil trapped, so that you cannot produce anymore. That's called the residual oil saturation or irreducible saturation point. Residual saturation. So I think the next slide has more. You can understand more from here. I think this is okay. This is still a mercury injection, but you can just use it as a oil saturation. Doesn't matter. So it's a non-wetting fluid, or it's a non-wetting fluid. So then let's start from here. So the water, the rock core is fully saturated with water. And when you inject the oil or the mercury to this rock core, it requires some amount of the pressure to displace the water in the rock core. It's called the displacement pressure. And as you increase, when you apply when you inject the oil with some displacement pressure, then water will be produced, right? Water will be displaced, and the oil will get into the rock. So the saturation will decrease as you go through here, and also the oil saturation will increase, right? Then at some point, no matter what, you increase the pressure, injection pressure, then there will be some irreducible water saturation. It's called the residual water saturation. And this irreducible water saturation is, there could be some pore, for example, this kind of a pore. You may have some water absorbed on rock mineral, right? Or maybe like the clay. In the case of clay, it wants to absorb the water, right? So that kind of a water is called the irreducible water saturation. That causes the irreducible water saturation. And if it's a well salted sand, so the pore size is pretty uniform. You have a type 1 graph, a curve here, and as you go toward to 1, 2, 3, for pore size distribution becomes wider. So let's think about the pore size distribution. This is case for the 1, and this is the case for 3. So in the case of 3, the rock core may have a small pores and medium-sized pores and large pores distributed. In the case of 1, the rock core will have a uniform sized pores. Okay. I think this is pretty similar to the water and air system. So water and air system and the water and oil system, they have very similar characteristics. And in soil mechanics, for the very near surface, we have unsaturated soil mechanics, right? And depending on the saturation, it has different stages. So this is the case when the saturation, water saturation is 1, and it's a perfectly dry case. And as you dry the fully saturated soil, this is the fully saturated case, and at some point air starts to invade, right? And it's called the funicular phase. Then, when the water saturation is lower than 8%, you have a pendular state. So then now the air is occupying the more space than the water. So here you have a air percolation, and here you have a water percolation. So water and air system, if you are familiar with the unsaturated soil mechanics, this concept can be also applied to the oil and water system. 혹시 질문, question? 궁금한 거? 없습니까? Okay, so then how can we measure the capillary pressure? So we're gonna see the methods to measure the capillary pressure. The most widely used method is the porous plate method or the porous disc method. Anyone have done the SWCC test? SWCC test 해본 사람 있나? 있나? 혹은 뭐지? 이게 디스크 놓고 이렇게 달아가지고 하는 것도 있지 않나? 그거랑 똑같습니다. 그러니까, so this is the same that we do in the geotechnical engineering for the SWCC test. So you have a disc, the ceramic disc with the very fine pores, with the small pore, and so this is fully wetted with the water. Then when you inject the air cannot penetrate this porous disc, right? So then you can measure only the volume of the water coming out of the sample with the pressure. So the same concept, and I think we've learned the origin of the petroleum and the petroleum reservoir. Reservoir is originally wetted or saturated with brine, and then there's a petroleum migrated to the reservoir, right? So hydrocarbon reservoir were initially saturated with water, and then the water hydrocarbon displaces the water, and it becomes the hydrocarbon reservoir. The pressure required for equilibrium displacement of the wetting phase within the non-wetting gas or the oil is the water drainage capillary pressure. And this is recorded as function of the water saturation. I will tell you how we can measure the capillary pressure with the water saturation. So here, this is brine. So this is maybe it could be a formation water or the salt water, brine. And you have a disc here. And this disc is also saturated with the brine. And the core is also saturated with brine. So all the brine phases are connected to here. And this is kind of a gauge, right? You see it. You measure the level of the volume change. And when you inject the oil, so here they use the crude oil, you will fill the remaining volume in the chamber. And this will give you the bulk volume of the sample. Right? And then when you increase the pressure to inject more and more, and then this brine will be displaced. Because there's no other escaping area, right? So the brine will just flow out to the bottom through this porous disc. And then you can measure the change in volume with this manometer. So you increase the pressure and you measure the volume of the brine came out, displaced from the rock wall. And for another pressure increment, you do the same measurement. Right? Then from this volume of water displaced, what can you calculate. You can calculate the oil saturation in the rock core and also the remaining water saturation in the rock core. And then what is this disk for? Disk is for protecting the oil, or keeping the oil inside the chamber. Right? You don't want to, as you increase the pressure, you don't want this oil going into here and changing the volume here. Right? So the oil is kept above this level of the ceramic disc, and only brine can move up and down. So the porous disc has a finer pore than the rock sample, and permeability of the disc should be at least 10 times less than the permeability of the core. So you have to choose the right disc, this porous disc, to measure the proper pressure. And I think the same concept and just different configuration. Here they use this as gas. So they are measuring the brine and gas capillary pressure in this case. And you have a core saturated with brine and you are injecting gas, or it could be air, and measuring the brine, the volume of the brine displaced for the given pressure. Okay. Okay, this is the same concept with just a little bit different configuration. So then what do we get? We get the pressure versus the water saturation curve. In the water wet system, let's say that you have a rock core or the soil which is fully saturated with water, and that when you want to displace the water out, you have to blow it, right? For example, you're injecting air. The air should have some pressure to be able to displace the water. Then a final pressure is required before any water is displaced. This is called the displacement pressure. So here, displacement pressure CT, displacement capillary pressure is here. And then it starts to decrease as you increase the pressure. This water saturation starts to decrease, and then this is the point that you have residual water saturation. And when you decrease it, it's going to suck up the water again, and then it will go to here. This is for the residual oil saturation. Actually, 1 minus residual oil saturation, or residual air saturation if you use the air. And this is the case for the water wet. In the oil wet system, what happens? Let's go back here. If this is this is better. If the rock core here is the oil wet system and it's fully saturated with water, then as soon as this rock core is in contact with oil, because the rock prefers to have the oil, right? They will soak up, they will absorb the oil from the outside without any pressure. Right? And then the water will be displaced, so that you can see that at the capillary pressure 0, it decreases to up to here, just by contacting with the oil, right? Because the rock wants to be coated by the oil. Then, as you increase the pressure, it will just go here, and this is the residual water saturation. And then, when you decrease the pressure, it comes to here, the residual oil saturation. The water system and the oil system. 혹시 질문? So it's a very important concept. Porous plate, the advantages and disadvantages are here, and advantages are at least one representative fluid is in place. So we are using the brine so that the brine and mineral interaction will be similar to the case that in the reservoir. And this is a large advantage over the mercury method, which cannot take account of clay water interaction. But the porous plate method is time consuming. It needs up to 20 days for equilibrium at each pressure. So sometimes when you have a very low permeability rock core, then it requires a lot of time for each pressure step. And capillary contact with the porous plate may be lost at high pressure, and this causes error. And imbibition is difficult to be obtained. And you can also do it under the confining pressure, and you can also inject the oil. Here you have a core plug, and this is the kind of a triaxial system. So you can apply the confining pressure with the rubber sleeve, over the rubber sleeve, and you have a porous disc again, and you can inject the oil, and you can measure the volume of the brine displaced. It's the same. And Hessler cell is called Hessler cell. And the other method is the mercury injection method. This is the popular method in geomechanics and in reservoir engineering. So you have a dry sample in a vacuum chamber, and then you inject the mercury into the chamber, right? And mercury is heavier than the rock core, so the rock core floats. And without any pressure applied, mercury will just cover and envelop the rock core. And when you increase the pressure, the mercury will start to invade into the rock core, and you measure the volume of the mercury injected with the pressure. So it's the same concept, but you use the mercury as a non-emitting fluid. Mercury injection method is convenient method for obtaining capillary pressure curve of rock exhibiting a maximum capillary pressure less than 1000 psi. And it can be modified for the high capillary pressure up to 60,000 psi. So the advantage of this method is that you don't need to have the porous disc. Porous discs actually have a limitation for the capillary pressure, upper limit for the capillary pressure. But with this mercury injection method, you don't need a porous plate, so there's no upper bound for the capillary pressure. So before test, the core is cleaned to remove the hydrocarbon and water and dried in vacuum chamber. And incremental quantities of mercury are injected while the injection is recorded. The volume injected is plotted versus pressure. And the main disadvantage of the mercury injection method is that once you use this rock core for the mercury injection test, you cannot use it anymore because it's contaminated with mercury. So you cannot wash it out. So this is a destructive method. And the same concept, so maybe this is the okay. Here you have a this is water for the air saturation, and you need to apply the threshold pressure for the initial invasion of the mercury, and this pressure is to conform to the exterior roughness of the sample. So if your sample is like this, and mercury is just covering up, and when you apply it, the volume change will occur because you have a better contact with the rock core, so that's the threshold pressure required for it. And then you increase the pressure, and this will invade into the rock wall to a certain point, that's the residual water saturation or the irreducible saturation. And then when you decrease the pressure, you follow this line, and you do the same pressure increasing cycle. So, and this second line and the third line will make a closed loop showing the hysteresis. So withdrawal of the mercury and the re-injection of the mercury, 2 and 3, is the characteristic capillary pressure curve. So this 2 and 3 is the curve that you want to get, you want to obtain for a rock wall. Disadvantage of the mercury injection method is the mercury is a non-wetting fluid, the air is the wetting phase being displaced by the mercury. And in order to convert the data to represent the water gas or the water oil system, the values of the surface tension and the contact angle are required at the temperature and pressure to be considered. So here the curve, here the capillary pressure curve here is for the actually the mercury and the air, right? And to apply for the reservoir condition, you want to have the capillary pressure for the oil and the water. Right? So you have to convert it from this mercury and air capillary pressure to the oil and water capillary pressure. So then you need to know the surface tension and the contact angle for the rock wall. That's the main disadvantage. But if you know these two values, it's very easy to calibrate because the radius of the rock will be the same. So the rock, the capillary radius will be P sigma cosine theta over PC. And this PC will be the same for any liquid, right? 2 theta cosine theta and PC. So if this is mercury and air and mercury and air, you can convert it to maybe water and oil, water and oil, and water and oil. Right? And this equation is fundamentally the same as this equation. So this is the capillary pressure for water and oil, and water and oil, the interfacial tension and contact angle. And this is water and air, and water and air. And this is the mercury and air, and mercury and air. So when you have a capillary pressure curve from the mercury injection method, you just need to convert the capillary pressure for the oil and water using this equation. So, and then this mercury injection method result can be used to obtain the pore size distribution of the rock. So this is the one example. You have a cumulative volume of the mercury injected for the pore throat radius. Then you can have this kind of a pore size distribution curve. So it shows that maybe median value of the pore throat is about 1 micron, and you have some pores with the more than 10 micron size, and you have some pores less than, how much is it? 0.1 micron, so then 100 nanometers. So kind of a same, maybe you can think of the particle size distribution curve, right? It's similar to this one. Okay. And from the capillary pressure, the capillary number can be calculated, and capillary number is a dimensionless value. that represents the ratio of the viscous force to interfacial force affecting the fluid flow in porous media. And when you think about the water displacement of the oil, the capillary number is defined as this. So this is the case. You have a rock core, oil-saturated rock core, and injecting water to produce the oil. So then you use the viscosity of the water, and U is the velocity, and the P is porosity, and the sigma is the interfacial tension. And capillary number for the field water flooding in the reservoir ranges from 10 to negative 6 to 10 to the negative 4. And capillary number has a marked influence on the ultimate recovery of the oil. And microscopic displacement efficiency is defined as this one. So then if the oil is recovered in full, then I think 1 minus IW is the oil saturation at full. So 1 is the fully recovered case. So you don't have any oil left in the rock core. And 0 is when there is no anymore any production of the oil. ED will range from 0 to 1. So then here, when the capillary number, let's look at this graph, displacement efficiency, ED or the EM or ED, is about 50%. Right? When the capillary number is 10 to the negative 5. So that means that only the 50% of the oil in the rock core has been produced. You have still the 50% of the oil left in the rock. When you apply this capillary number, when you apply the fluid with this flow with this capillary number, and as you increase the capillary number, you have increase in production, oil production. Right? So when the capillary number is less than 10 to the negative 4, there is no noticeable effect on the displacement efficiency in this region. Right? And as the capillary number becomes larger than 10 to the negative 4, now it's proportional to the capillary number, right? So oil production is increased with the higher capillary number. And lower capillary number means what? It's a capillary, let's look at this definition. Lower capillary number means that the interfacial tension is dominant, and the higher capillary number means that the viscosity is dominant. So when the capillary number is less than 10 to the negative 4, capillary force is dominant, the capillary dominant regime. And when the capillary number is larger than that, then it's a viscous force dominant regime. It begins to increase with ED. And when the capillary number is larger than 10 to the negative 2, and displacement efficiency becomes almost 1, that means the complete displacement of the oil has been occurred. So when the capillary number is less than this one, so when in this region, capillary dominant region, oil displacement occurs by the movement of the oil ganglia, which are several pore diameter in length. And residual saturation is distributed as isolated droplets and the groups. So in this region, if we imagine rock core, and the oil is moving as a droplet. This is oil. When you flush it with water, like this. If some oil is trapped here, then it will be presented as an isolated droplet. So, and to increase the capillary number, what can we do? Because we want to increase the capillary number to produce more oil, right? What can we do? We have a capillary number, U, V, Q, interfacial tension. To increase the NC, we can decrease the viscosity. So increase the viscosity, and velocity, we can increase the velocity, or we can decrease the interfacial tension, right? So this is the EOR, the enhanced oil recovery method, actually. So we can inject some surfactant to reduce the interfacial tension, and you have a more oil production. And you can inject the water with higher flow velocity, then capillary number will increase, and it will sweep and push out the oil more. Okay, example, very simple. Calculate the capillary number and the pressure gradient for the flow at the given velocity. And the information, the fluid viscosity is 120 cp, interfacial tension here, and velocity is here. So this is the day. And porosity, absolute permeability, and relative permeability. So calculate the capillary number first and see that what U V over sigma. We don't want to, I'll give it only 2 minutes. What's the SI unit for centipoise? Pascal second? 10 to the negative 3, right? And velocity meter per day times 24 hours, 60 minutes, 60 seconds. What's the other way? Second. And this will give you some value, right? How much do we have? Okay, what's the capillary number you get? 한가랑? 그러면 36. 아닐걸? Anyone have different value? 1. 지금 많이 가세요? 1.46, 1.46 times 10 to the negative 4. Actually. That was my answer. And once you have the capillary number, and the second question is, what will be the pressure gradient to have this capillary number and satisfying this fluid velocity? Then we can apply the Darcy's law and replace this velocity term with the Darcy's law. Then, what's Darcy's law? Okay. P over L. The area is gone and the mu is here, right? So then, velocity, we can plug it here. Then it becomes this equation. Right? Then delta P, so we want to get the pressure gradient, delta P over L. I think we can get it from here directly, right? Velocity times mu over K RW times K. Yeah. So then, just the same, right? So you can plug the number. This is the viscosity, and the velocity is 1.68 divided by 24, 60, 60, right? Meter per second. And then relative permeability. The reason that we are multiplying this relative permeability and absolute permeability is that we want to get the effective permeability of the fluid, right? So 0.21 times 60 times 12 meter square. So here is a micrometer square. So this is 10 to the negative 12 meter square. And then I think you will get the pressure gradient, delta P over L, as a Pascal per meter in the end. So if you cancel out, the second is cancel out, and the meter here, right? And then you have a Pascal per meter. Then the value is about 7.5 10 to the 4 Pascal per meter. Okay. Question 혹시 질문 있니? Okay. Let's talk about only the one method for the wettability. There are like 2 or 3 methods that we're gonna cover, but because of the time limit, let's talk about the Cecil-Duran measurement of the contact angle. So this is the very straightforward method. So you need to have a polished flat surface. Then you make a droplet of the fluid that you want to measure. And then take a picture and then draw a line that's tangent to to the droplet, then you can measure the contact angle. So here, the smooth and homogeneous surface is necessary. So in this case, we use the quartz, and this is the gas, and here's the water. So because the gas is lighter, they float. So in this case, the surface was at the top. And contact angle is measured through the denser phase. So which one is denser? The water is denser, right? So when you draw the line from the contact point between the surface and the gas and the water, and you draw a line tangent to the gas droplet, and then this is the contact angle, theta. And you measure like 8 to 10 points because the surface can be heterogeneous. And then you do the average. You do, take the mean value of each and all the data points. And advancing and receding contact angle can be also obtained for the hysteresis with respect to surface area. So this is the Cecil droplet method. And solid here, and you have a liquid which is denser than the liquid above it. Right? So then contact angle from here to here. I think that this is the water and the oil. Right? And then this will be a hydrophilic, neutrally wet, hydrophobic. Right? The oil wet. And could be an opposite case. You have an oil droplet surrounded by water. In this case, you measure the contact angle through the denser phase. So theta is less than 90 degrees still, and it's a water wet case, neutrally wet, and the oil wet case. So doesn't matter whether you measure it with the water droplet surrounded by oil, or you measure it with the oil droplet surrounded by water, you should obtain the same contact angle value, because the convention is you measure it through the denser phase. Okay, question? We'll continue from here from the next class. That will be next Monday. Huh? And then we'll cover the relative permeability. So if you have time, please read the class notes by the Dr. Paul Glover and the Petrophysics chapter 5 and 6. Huh?